Last lesson, we learned to perform hypothesis testing on a population parameter, either the mean for a quantitative variable or the proportion for a categorical variable by using a random sample extracted from the population. In this video, we will expand our knowledge of inferential statistics by considering a scenario in which we compare the means of two samples extracted from two independent populations. Let's suppose we have two populations. The first one has mean mu1, and the second one has mean mu2. Further, let's define the respective population standard deviations as sigma1 and sigma2. We really don't know the shape of these populations' distributions, but so long as we draw random samples from each, and each sample is composed by at least 40 observations, then all the assumptions for inference are satisfied, and we can build the sampling distribution for the difference of two means as a normal model. In Lesson 2, we learned that we can calculate the expected value of the sum or difference of two random variables simply as the sum or difference of the respective expected values. So it stands to reason that such sampling distribution for the difference of two means will be centered at the difference of the population means, or mu1 minus mu2. In Lesson 2, we also learned that when two random variables are independent from each other, then the variance of their sum, or difference, is always expressed as the sum, and never the difference, of the respective variances. But in our case, because the two samples are drawn from two independent populations, then we can write the variance for the sampling distribution of the difference of two means as the sum of the variances for the sampling distribution of each mean. Because the standard deviation is the square root of the variance, and we already learned in the last few lessons the formula for the standard deviation of the sampling distribution for the mean, which is sigma divided by the square root for the sample size, we can now write a standard deviation for the sampling distribution of the difference of two means as follows. However, we already know that often the population standard deviations are unknown, so we should replace those quantities with the respective sample standard deviations and calculate the standard errors instead. There you go. Now that we have defined a sampling distribution for the difference of two means, we can begin performing a hypothesis testing and building confidence intervals in the case of two independent samples. The test of hypothesis in the case of two independent means, when the population standard deviations are unknown, is called the two-sample t-test. As we learned last lesson, we can have one or two-tailed tests, depending on whether we are testing for an increase, a right-tailed test, a decrease, a left-tailed test, or a change, a two-tailed test. If we are conducting a two-tailed test, then the null hypothesis will presume that the two population means are, for example, equal to each other. So we can write h sub index 0 colon mu1 minus mu2 equal to 0, and for the alternative hypothesis we have ha colon mu1 minus mu2 not equal to 0. The sampling distribution for the difference of two means will be centered at 0, our null hypothesis, and will have a standard error as shown earlier. We can now calculate the test statistic t as a ratio where at the numerator we have the difference of the sample means, x1 bar minus x2 bar, minus the difference of the population means, which we have assumed to be 0, and at the denominator, the standard error for the sampling distribution of the difference of two means. We can now calculate the p-value as the sum of the areas on the tails outside of the test statistic and its symmetric counterpart, or twice the right tail outside of the test statistic, which in Excel can be computed plugging in the test statistic in the t-dist formula for a student's t-distribution. And that's where things get a little complicated because the formula for degrees of freedom in the case of two independent samples, as you can see, is not for the faint of heart. But fear not, as we don't have to build such a complicated formula in Excel. To carry out the two-sample t-test, we can use the Excel data analysis tool pack instead, so long as we have the samples data sets. To locate the data analysis tool pack in Excel, you should select the Data tab and then look for Data Analysis all the way to the right of the ribbon in the Analysis group. If you don't see a data analysis button, it means that you never installed it before. To install the data analysis tool pack, please follow these simple steps. Select the File tab. Select Options at the bottom of the left-hand side File menu. Select Add-ins near the bottom of the left-hand side Options menu. At the bottom of the window, you will see a drop-down menu that says Manage Excel Add-ins. Select Go and locate and check the Analysis Tool Pack box. Select OK and return to the Data tab. The Data Analysis button should now be there. Now, let's practice on Excel by considering the following example. Let's suppose you have been promoted to Senior Manager of Credit Card Operations for a large Fortune 500 financial institution. Congratulations. As part of your new role, your director has assigned you the task of checking the feasibility of a new credit card promotion meant to boost credit card spending, such as 5% cashback on purchases or double miles on your favorite frequent flyer programs, or whatever your manager's heart desires. To test this new credit card promotion, you send the promotion information to one sample of 50 random customers. And 3 months later, you collect the spending of these 50 customers, and then collect the credit card spending during the same time period of another random control sample, also of 50 customers, who obviously is oblivious as to the existence of such promotion. Question is, has the promotion increased credit card spending? Let's test this question with a two-sample t-test. And because we are looking for an increase in spending, then we need to build a right-tail test. First, the null and alternative hypothesis. H0, mu promotion minus mu control less than or equal to 0. The null hypothesis encompasses all scenarios where the promotion failed to increase credit card spending. HA, mu promotion minus mu control greater than 0. The alternative hypothesis contains all the other scenarios where the promotion increased credit card spending. Because the two samples contain at least 50 random customers each, then all the inferential conditions are respected, and we can build a normally distributed sampling distribution for the difference of two means. Now, we need data. You should have been given access to the creditcardpromotion.xlsx file. If not, please pause this video, check your notes, and locate the data file before proceeding. Open the Excel file and select the first worksheet, labeled Independent. This worksheet contains the credit card spending for the two samples of customers, 50 for the promotion and 50 for the control. Let's go ahead and run this test with the Data Analysis Tool Pack. Select the Data Analysis button and scroll all the way down until you find t-test, two samples assuming unequal variances. Select OK. Now select the variable ranges for the two samples. Be mindful that the test is computed in Excel as the mean of sample 1 minus the mean of sample 2. Because we set the null hypothesis as mu promotion minus mu control, then it stands to reason that we must populate the control sample in range in column B for variable 2 and the promotion sample in range of column A for variable 1. Note that row 1 contains the samples label, so make sure to check the box labels as well. Enter 0 for the null hypothesis and keep alpha, the significance level, equal to the default value of 0.05. Because this is a small worksheet, under Output Options, select the radio button output range and type in or select an empty cell in the worksheet where you can display the results of the test. There is no need to show the results in a separate worksheet. Run the test. The output contains two columns of statistics, one for each sample. At the top, you have the summarized sample means, sample variances, and sample sizes. The sample standard deviations are not shown, but they can be easily computed if needed by taking the square root of the sample variances. Then, past the null hypothesis, you have listed the degrees of freedom, which, as you can see, it is slightly less than a sum of the sample sizes, but not so trivial as the sum of the sample sizes minus 1. Then the standard error is not provided, but it can be easily computed as the square root of the sum of the ratio between the sample variances and the respective sample sizes. Or $51.5. The test statistic is the ratio between the difference of the sample means and the standard error, or 2.565. You are then given the p-value and t-critical for both a one-tailed test scenario, which is our case, and a two-tailed scenario where the p-value is just twice as large as it is for the one-tailed test. Because the p-value is less than the significance level, we reject the null hypothesis and conclude that the promotion will increase credit card spending. Now that we have all the necessary statistics in the test output, we can also calculate the confidence interval for the difference of two population means. If you recollect from Lesson 5, a confidence interval is an estimate of a population parameter, and it is defined as the point estimate plus and minus the margin of error, which was defined as the product of the t-critical, not z because sigmas are unknown, times the standard error. In our case, the point estimate is simply the difference of the two sample means. The t-critical at a given confidence level depends on the degrees of freedom, and it is already provided by the test output as 1.661. And the standard error we need is the standard error for the sampling distribution of two means, which we have already determined. Plugging in the numbers, we obtain a confidence interval at a 90% confidence level, not 95, for the difference of two population means between $46.5 and $217.6. As you can see, the confidence interval does not contain zero, the null hypothesis, confirming our earlier conclusion to reject it. Well, that's great. You've just concluded that promotion increases spending, but should you launch it? What if your directory informed you that the cost of the promotion is of $100 per customer in average? So now the question becomes, is the promotion profitable? To consider this follow-up question, let's modify the null and alternative hypothesis so that rather than setting the null hypothesis less than or equal to 0, we set it to less than or equal to a parameter d0, which in our case is the cost of the promotion, $100. And the alternative hypothesis to greater than d0 or $100. The math here changes slightly because now the sampling distribution is centered around d0, which is $100, and even though the standard error remains the same, the test statistic will have to be computed as follows. What will be the p-value now? All you have to do is to go back to the data analysis t-test and modify the hypothesized mean difference to 100. If you don't want to override the previous results, have a care to locate the new output elsewhere on your worksheet, such as underneath the previous output in cell D15. But because we moved the sampling distribution to a difference of the means of $100, the difference of the sample means, our test statistic, is now much lower than it was before. Consequently, the new p-value is now greater than alpha. Therefore, we fail to reject the null hypothesis and cannot conclude that a credit card promotion will be profitable. Before we conclude this video, I want to make sure that you realize a few things. Number one, we already knew that the promotion was not profitable when we computed the confidence interval for the population mean spending increase. Because the lower bound of the confidence interval was only $46.5, it follows that $100, the null hypothesis, is contained within the confidence interval limits. In other words, there is a considerable probability that should we launch the promotion, we would not increase spending enough to make the promotion profitable. And what is such probability? It is the probability of a type 1 error, which is the p-value, or about 27%. Number two, note that we did not conclude that the promotion will not be profitable. That would have meant accepting the null hypothesis. We simply said that we can't be overly confident that it will be profitable. Number three, you may have noticed other two t-tests in the data analysis toolpack next to the one we just used to perform the two-sample t-test, besides, of course, a z-test. The z-test, two samples for means, is the version of the test we just described when the population standard deviations are known. As described earlier, this test has little practical significance, and I chose not to describe it to you. One of the other tests is called the t-test two-sample assuming equal variances. This test is described in most statistical textbooks as the pooled t-test. The pooled t-test assumes that both standard deviations are very similar to each other. Even though this may be a reasonable assumption to make in some case, it is also of little practical significance, and I chose not to teach this one either. The remaining t-test paired two-sample for means will be the subject of the next video.